Good afternoon, everybody. My name is Dmitry Tolmachov, and I am a PhD student at ETH Zurich in Switzerland. My presentation is titled VkFFT and Beyond, a platform for runtime GPU code generation. Unfortunately, I couldn't get a UK visa in time to participate in person, so I had to make a recording of my talk. I will still be happy to answer any questions afterwards via email. In today's presentation, I will talk about the new major release of VkFFT library and the new platform for runtime GPU code generation it introduces. I will also show how VkFFT works on the inside and how GPU code can be optimized. Then we will briefly talk about the future of VkFFT. After this, I will showcase how a finite difference solver can be implemented within the framework of the developed platform, with the benchmarks for different accuracy orders and precision of modern HPC GPUs, such as NVIDIA A100 and AMD MI250, and a consumer-level GPU, such as NVIDIA 2080. Firstly, let's have a few words on what a fast Fourier transform is. Discrete Fourier transform is a well-known operation in signal processing that allows to obtain the frequency domain representation of the original discrete function. The fastest known algorithm for evaluating the DFT is known as fast Fourier transform, shortly FFT. The Cooley-Tukey algorithm reformulates a composite-sized DFT as a combination of two DFTs. The steps required to do so are, firstly, perform bit reversal permutation to reorder the data. Then we perform N1 DFTs of size N2. Then we perform a linear number of multiplications by twiddle factors, complex roots of unity defined by the radix. And in the end, we perform N2 DFTs of size N1. Recursively applying this algorithm, we obtain an n log n complexity compared to squared complexity of direct multiplication if we compute DFT according to its definition. The main focus of this talk, the VkFFT library, is an FFT library optimized for modern GPUs. It supports multidimensional systems, forward and inverse directions of fast Fourier transforms, and can do big FFTs with sizes up to 2 to the power of 32 in all dimensions. VkFFT has optimized radix kernels for all primes up to 13 and composite radix kernel support. For all other sequences, VkFFT incorporates Rader's and Bluestein's FFT algorithms. VkFFT supports single, double, and half precision calculations. VkFFT can do complex to complex, real to complex, and complex to real transformations. And now it also supports real to real discrete cosine transformations of types 1, 2, 3, and 4. VkFFT can perform optimized convolutions and cross-correlations and do native zero padding to model open systems. VkFFT works on NVIDIA, AMD, Intel, Apple, and mobile GPUs. It works on Windows, Linux, and macOS, and supports Vulkan, CUDA, HEAP, OpenCL, Level 0, and Metal as backends. In the new major release of VkFFT, version 1.3, I address the issues of the single header approach. Code is once again fully reorganized in multiple headers, but the codebase is still C, not C++. This update removes a big portion of code duplication and standardizes the code generation. Previously, the code generation had big chunks of hard-lined sprintf calls, and now all operations have a dedicated function call to them. All these modifications form a new platform for code generation, which I will now describe. The new platform implemented has a following modular structure. The user of it interacts with the application manager that handles input configuration parsing, the binaries, and GPU resources. It then calls for the plan manager to perform plans initialization. The plan manager performs an optimization of parameters such as number of threads, shared memory usage, and loot allocations. It does so for a particular task and GPU architecture, and then calls for the code manager. Code manager does GPU kernel code generation. It produces a single kernel for the task defined by the plan manager, which is then compiled by the plan manager. with the help of just-in-time compilers. The code manager also has multiple level structure inside, which facilitates algorithm code reuse. The level 2 kernels contain a clear description of the problem via a sequence of calls to lower levels. These kernels also perform kernel layout configuration. Level 1 kernels have simple routines such as matrix vector multiplications, FFTs, pre- and post-processing, and read-write blocks. The lowest level 0 kernels are responsible for memory management, basic math functions inlining, subgroup functions, and API-dependent definitions. The 1.3 version of VkFFT also introduces container abstractions. The code generator now operates on special data containers implemented as C unions that can hold integer, float, complex numbers, either as known during the plan creation values or as strings of variable names. An example of this is a mul operation that performs a multiplication. It can be defined as A equals B multiplied by C. If all containers have known values, A can be pre-computed during the plan creation. If A, B, and C are, for example, register names, we print to the kernel an operation of multiplication. Each operation, like mul, has its own representation for all supported APIs. An important distinction is that it is not a full compiler, but a simple tool that unifies syntaxes of different APIs and supports just-in-time optimizations. Like what VkFFT is already, but cleaner. On this slide, I show the simple kernel generated by VkFFT for a Fourier transform of length 2 in OpenCL and CUDA APIs. Note that it is not a particularly good FFT length to run on a GPU, as it is too small, but it is a good example of VkFFT kernel code structure, as it will be fairly similar for more complicated kernels. We start with the description of the buffers used by the kernel. Then we define all the registers and indexes that we will need. After that, we have a read block and a pre-processing block. Then we have a main FFT loop, post-processing block, and a data write block. As can be seen, the code generated by VkFFT is simplified as much as possible. There is only one simple operation per line, almost everywhere. Now we will dive into how exactly VkFFT works, starting with the main FFT loop. All algorithms in VkFFT are based on the Stockholm version of the fast Fourier transform. In the Cooley-Tukey algorithm, digit reversal is performed once, before or after all steps of the recursive algorithm, while in the Stockholm algorithm, the digit reversals are done after each small radix 2 to 13 FFT. The main FFT loop can be considered as the core of VkFFT and the place where most compute power is used. VkFFT follows the conception of one thread, one small radix Fourier transform. An example of this, FFT of length 35. The notation on this slide means 7 threads perform radix 5, R5 Fourier transform. Then 7 threads write to shared memory, synchronize, and 5 threads read from shared memory. 2 threads are there inactive. Then 5 threads perform radix 7, R7 Fourier transform. 2 threads are again inactive. In this example, the kernel configuration will have 7 threads with 7 complex variables in registers. VkFFT has 6 primes implemented as a single thread small f Fourier transforms, 2, 3, 5, 7, 11, and 13. VkFFT also has single thread FFT codelets for small prime multiplications, such as 4, 6, 8, 9, 10, 12, 14, 15, 16, and 32. Bigger primes can also be implemented as a single thread Fourier transform, but this reduces total number of threads per kernel and occupancy as a result. Let's discuss a problem here. Sizes like 26 will have a huge discrepancy between number of threads and used registers. There is a need for 13 threads with 2 complex registers to do radix 2 Fourier transform, but only 2 threads with 13 registers to do radix 13. The solution to this is to implement code that can have one thread do more than one small radix Fourier transform. Here, an FFT of length 26 can be done with 2 threads, each doing 7 Fourier transforms of length 2. 2 multiplied by 7 is 14 complex registers. One extra Fourier transform will not be used later. And 1 Fourier transform of length 13. Or this problem can also be done with 1 thread with 26 registers. There is a big room for fine-tuning. On this slide, we define the following control parameters. Mean registers per thread value is the lowest number of registers needed in all small radix kernels. Registers per thread value is the maximum number of registers needed across all small radix kernels. Each prime has the number of registers required for it on the range from mean register per thread to registers per thread. It is all handwritten for all combinations of primes from 2 to 13, total 64 combinations, to have similar low gap between mean registers per thread value and registers per thread value. So this results in having maximum number of threads working at every step. All this decision making is performed in the VkFFT scheduler header file. Now let's demonstrate the thread assignment logic on the FFT of length 240, which is a multiple of 16, 3 and 5. Here mean registers per thread value is equal to 10 and is used for radix 5 Fourier transform. Registers per thread value then is equal to 12 and is used for radix 2 and radix 3 Fourier transforms. As a result, the FFT of length 240 is split as 10 threads doing 6 radix 2 Fourier transforms, 10 threads doing 1 radix 12 Fourier transform, and 12 threads doing 1 radix 10 Fourier transform, as VkFFT has custom kernels for 10 and 12. Total number of threads per FFT is then determined as the FFT length divided by the mean registers per thread value and rounded up. In the example above, FFT of length 240 will use 24 threads. Here we have a problem. An FFT of length 240 will need only 24 threads, which is smaller than the seamed warp or wave size of most modern architectures, 32 or 64. The solution to this is to have a kernel do 5 fast Fourier transforms of length 240. This way we have 120 threads and almost full warp utilization. The batching of FFTs mentioned on the previous slide can be done in an outermost or in an innermost dimension in the shared memory. This can solve potential shared memory bank conflicts with the common approach of having non-power of 2 strides. Overall, thread block structure is 2-dimensional in the main FFT loop, threads required per FFT in one dimension and number of FFTs in the other. The image below demonstrates the described layout of data in the shared memory. Primes like 17, 19 and bigger deserve a special mention. VkFFT now has a Rudder's FFT algorithm, which allows to view these primes FFTs as a prime -1 length convolutions, which can be done as an FFT, kernel multiplication, and an inverse fast Fourier transform. For example, of FFT of length 272, which is a multiplication of 17 and 16, we can do it as 16 FFTs of length 16 twice, which is Rudder's algorithm, and then 17 FFTs of length 16. Another example is FFT of length 116, which is a multiplication of 29 and 4. It can be done as 28 FFTs of length 4, then 16 FFTs of length 7, we do these operations twice, and then we do 29 FFTs of length 4. As can be seen, Rudder's FFT algorithm allows to do big primes with the same logarithmic complexity as regular FFTs, but with 2 times the shared memory transfers and multiplication kernel transfer costs. Below, the layout of Rudder FFT algorithm is given. Now we move on to the read-write stage of VkFFT. Because FFT is a memory-bound problem, this stage is just as important as the main FFT loop stage. We start with describing the memory speed hierarchy of modern GPUs. The main principle here is the closer something is located to the cores, the faster the core's access to it will be, and the smaller the size of it. So the priority of optimizations should go from the bottom to the top. First we reduce system memory transfers as much as possible, then global memory transfers, and then we optimize shared memory transfers. It is worth noting that modern GPUs have tens of thousands of cores and usually can perform 10 to 100 mathematical operations per single global memory request. So at times it is beneficial to just recalculate the value then store it. On this slide, I will describe how VkFFT handles global memory communications. VkFFT is designed to have as few global memory transfers as possible. VkFFT kernels also use all available threads to read-write data as continuously as possible. Memory coalescing is the priority here. Instead of the 2D approach of the main FFT loop, they are viewed as a 1D pool here. There are two types of read-write operations in VkFFT, non-strided and strided. First works with the continuous data in memory, as can be seen on the image below. Second operates on small chunks of data needed for coalescing, but from distant addresses. These layouts allow to fully utilize the global memory bus without having to transpose the data. Now let's move to the platform implementation of the read-write stage. All memory operations are abstracted with the help of VkFFT containers, just like math operations. If the layout of the memory operations is the same as the first or last FFT operation, which means each thread reads data that it will use, read-write can be performed directly to registers, otherwise data is written to shared memory. Zero padding is also done at this stage as a conditional check. In VkFFT version 1.3, read-write stage has been generalized and optimized. Before, there was separate code written for all complex-to-complex, real-to-complex, complex-to-real, or real-to-real transformations. Total of 10,000 lines of code. Now it is only 1,500 lines of code. Another known problem that is worth focusing on is that extremely distant, more than 100 megabytes, coalesced memory accesses can hit the same pin of the memory controller and become serialized. The only workaround here is to coalesce more FFTs per kernel, even potentially increasing memory transfer by having more uploads. Another big two stages of the VkFFT kernel are pre- and post-processing. In version 1.3, all pre- and post-processing blocks have been rewritten to follow strict rules imposed by the read-write stage. They can work either with the continuous 1D addressing of read-write stage or with the 2D approach of the main FFT loop. If the pre- and post-processing requires shared memory communications, it can switch from one addressing mode to another, potentially saving on shared memory data transfers. If pre- or post-processing is not shared memory localized, it can be done as a separate plan with separate dispatch and code generator. An example of this is an even real-to-complex, complex-to-real decomposition algorithm for big sequences. Now we will briefly talk about the potential VkFFT future, which may very well be a direct binary generation. Why I would like to do this? Firstly, for FMA operations, the code of VkFFT kernels is already looking similar to NVIDIA SAS or AMD ESA. As for the indexing, VkFFT tries to calculate addresses with as few instructions as possible, but at times it backfires. An example of this occurs when a compiler, NVCC or HipCC for example, understands that kernel has the same addresses during the read stage and during the write stage, and keeps them for the whole execution time in registers, increasing the number of registers used and potentially reducing occupancy. Another problem is that NVRTC, HipRTC, and other JIT compilers are slow. The sequence of VkFFT commands, however, is fast. With direct binary generation, it will be possible to generate optimized binaries with no overhead. I understand that all this may be very ambitious, but it can be an interesting thing to do. Let's move on to the platform showcase on an algorithm different to the FFT, namely the finite difference solver. To demonstrate that the platform is able to use the hardware at the lowest level, a finite difference solver that uses no shared memory for communications between threads has been implemented. A single working element in it is called a logic block, and it can be seen on the image below. It has a singular seamed size group of threads dedicated to it and has configurable dimensions which define the workload per one kernel. Each logic block contains all respective data from the main system in its threads registers. Each thread is responsible for all data in Y and Z dimension slice of the logic block, and if the nx is bigger than seamed size, every seamed size plus thread ID x-axis values as well. Total number of logic blocks is equal to the number of kernel dispatches. What is unusual in this approach is the low number of threads per kernel. Only seamed size number of threads, which is equal to 32 for NVIDIA and 64 for AMD. However, we have no synchronizations inside, so low number of threads is sufficient to cover latencies. Configurable size of logic block allows for fine-tuning of halo effects impact on data transfers, which will be seen on benchmarks later. Different logic block sizes also have different cache hit patterns, which are hard to estimate, which is another reason to have them tunable. Within the logic block, the only data transfers are subgroup shuffles along the x-axis, as all y and z-axis data resides in registers of a single thread. The simple shuffle operation can be seen below, and modern GPUs can do them directly in registers without a round trip to shared memory. On this slide, we will compare the performance of modern HPC GPUs, such as NVIDIA A100 and AMD MI250, and consumer-level GPU NVIDIA 2080. The task we perform is calculation of second derivatives on each axis for 3 real functions respectively, and then addition of all the results in single precision. The system is an evenly discretized cube. The benchmarks are provided for 2 different orders of accuracies. Second order, which uses 2 neighboring elements to calculate, and fourth order, which uses 4 neighboring elements. Having multiple axes helps to estimate the cache effects on the performance. On the image below, we see the dependence of the estimated bandwidth, calculated as 4 system sizes, 3 uploads and 1 download, divided by the execution time. And we check how it depends on the cube discretization. The bandwidth is not accurate as it doesn't account for additional data transfers related to halo effects on the logic blocks. However, it shows the peak value as we have to always do these 3 uploads of the input systems and 1 download of the result. Near each point you can see the best logic block dimensions for this particular configuration. As can be seen, different systems achieve best performance with different logic block configurations. This performance difference can reach 30% compared to the median solution across all results. For example, big systems such as 1024 cubed can no longer rely on L2 cache hits for Z-axis finite differences. It is most noticeable on NVIDIA GPUs. So it is beneficial to have bigger logic block Z size to have less requests. NVIDIA 2080 GPU has a very small L2 cache compared to other GPUs, so it benefits more from varying logic block size. Overall, all GPUs achieve up to 80% ratio of estimated bandwidth to the theoretical bandwidth of a GPU for second order scheme and 60% for fourth order. If we use the more sophisticated tools for profiling like NVIDIA NCU Profiler, we'll see that actual memory bus utilization is near 100% due to the cache misses related to the halo effects of logic blocks. Similar results are obtained in benchmarking of double precision systems, although the logic block optimizations have different best dimensions. The bandwidth is slightly better due to the fact that double precision takes twice as much localized memory. What is worth noting is that even NVIDIA 2080 that has a low double precision core count still remains bandwidth bound, even though compute pipeline usage jumps from 20% to 80%, as reported by the NCU Profiler. To summarize today's presentation, I showed a big redesign of VkFFT, which has already been released on a developed branch of the VkFFT GitHub, and will be merged into the main one after a couple months of thorough testing and optimizations. I also gave insights into how VkFFT works under the hood. It is also worth noting that the VkFFT white paper has been published in an open access journal, so everyone can check it out. Finally, I presented the platform of code generation based on the VkFFT design and demonstrated how low-level optimized finite difference solver can be implemented in it. Thank you all for your attention. I'm truly sorry that I couldn't be here in person, but I will be happy to answer all your questions over email.